everyone. Today we will have our lecture 23. We will continue our discussion on passivation. And in the last lecture, we could see that the passivation it was first experimentally shown by Michael Faraday in 1836 with the famous experiment of iron in HNO3 with the change in concentration of HNO3 and subsequently scratching of the iron block and then subsequent rapid corrosion. So, when iron is dipped in concentrated HNO3 at room temperature, it passivates, and then when it is taken to dilute acid, there is no change, but once we scratch the iron block in the dilute acid, the rapid corrosion starts. And then we also have witnessed some of the typical polarization curves what we come across while where passivation is observed, and there are three variants. One variance was like the graph what we have plotted. One variance was this is E and this is log I. One variance was like this, and the second variance was like this, and the third variance was like this. So, we also talked that this particular is a kind of a special situation we will discuss later, but these two cases we could see that there is a passive region and the passive zone is up to this particular region is the passive zone, and out of these two, this is spontaneous passivity, and this is active passive transition. And on both the cases we could see the passive region when we go into the anodic polarization side, because if we take this particular portion as well as this particular portion, both the cases metal is actually depositing, cathodic reaction is taking place. But if we go upward from this corrosion potential, this is E core, corrosion potential, we are actually going into the anodic side. So, this two zone we are having this reaction. So, that means passivity is achieved when we go to anodic side. This we talked, and then we also defined passivity is basically chemical inertness introduced into the metal when that metal is exposed to an environment due to its ennoblement or anodic polarization. There could be some other instances like lead, their ennoblement or passivation appears because of the lead sulphate formation in H2SO4. So, those cases we have considered. Now, before we talk more about passivation, there are some characteristic features of passivation or some of the informations which will be important for passivation. So, let us state those points. One is some metals they show passivation like copper, nickel, titanium, aluminum, then you have iron, these are the even molybdenum, even silicon, these are the elements they provide passivation. And if these are the elements undergo passivation easily, then of course, since these elements are easy for passivation, then if these elements are present in an alloy, that alloy is also susceptible, or ease of passivation in those alloys become easy. So, that means if these elements are present in an alloy, so that alloy means in the form of solid solution, that alloy is also can form passive alloy. Becomes easy. Then so when we have these alloys, then we can have loss of chemical reactivity by drastic reduction. It can go into active passive mode, that is this mode, or it can have spontaneous passivity, depending on whether the passive layer is already formed on the metal surface when we expose it to the environment, that electrolyte, or in some cases it could be nascent phase, and then in that electrolyte the passive layer forms. In case of active passive, one example is iron exposed to concentrated HNO3. So, there initially you will see bubbles, but after some time you will see that the bubbles formation stops and the weight loss becomes negligible. So, that is one case where active passive transition happens. In some of the cases you can experience this particular scenario, we will see later on. And there are so when we are talking about passivity, that means it is a formation of layers, okay, on the metal or alloy in the corrosive. Corrosive is nothing but the electrolyte where corrosion is highly possible. And what happens in these cases? So, if this is the metal surface, I can have a barrier film formation. This is barrier film, or one could have a barrier film. So, this is the metal surface and alloy surface. One can have a barrier film or layer. In addition to that, there could be a porous layer, porous deposit. In both the cases, it is easily understood that the metal surface, this is the metal surface, and here it is the metal surface. These are not exposed to electrolyte directly. So, here we have electrolyte. Here we have electrolyte. So, since the metal surface is not exposed to the electrolyte, so the dissolution of the metal will be decided by the ion transfer or ion migration through the barrier film or through the barrier film and porous deposits. So, the dissolution rate drops. And another interesting part is this barrier film dimension. If we consider, it has been observed that these are some few nanometers thick layer forms. Now, coming to the other aspects, since we are talking about barrier film, some of the elements in iron, they readily forms that barrier film, these particular elements when they present in the iron. For example, chromium. If we talk about chromium, it has been observed that in case of stainless steel, if we try to plot the corrosion rate, this is CR is nothing but the corrosion rate, and that if we want to plot with reference to the weight percent chromium, till it reaches to around 12 weight percent, the corrosion rate is pretty high, and as the concentration chromium increases gradually, so the corrosion rate drops and then it goes to very low value, which can be even less than 0.001 centimeter per year. Okay, so which is a very low corrosion rate, and that happens because we have Cr2O3 film formation. In case of aluminum, it is a Al2O3 that forms and which passivates aluminum. Now, interesting part is aluminum is also considered as an element, a metal which is used as a sacrificial anode. Now, as we have noticed in case of in the discussion when we talked about sacrificial anode, so the anode material should dissolve spontaneously, so that it provides required electrons for cathodic reaction on the cathodic surface, which is nothing but the iron, and that is what the iron is protected from corrosion. But aluminum, if it forms Al2O3, then it passivates, and once it passivates, then it may not be anodic to the iron surface. So, that is what in case of aluminum, when we use aluminum, we generally add bit of other elements like zinc, so that it does not allow that passivity to appear. That means, it does not allow aluminum oxide to form on the metal on the aluminum surface. So, it will remain anode all the time. Now, this is one part, and of course, in case of stainless steel, apart from chromium, we add nickel, we add molybdenum, even we can add titanium, niobium. So, those all elements would provide bit of extra passivity, or it can improve the passive layer, improve in order to have a better resistance to corrosion. When we talk about the improve the passive layer, means it can modify the oxide layer, so that the diffusion of ions, which is the metal ion, to come from the metal layer or metal oxide film layer to the metal electrolyte, to the oxide electrolyte interface. So, we have three interfaces. One interface is this is rather two interface. One is this is film, oxide film, this is metal, this is electrolyte. Fine. In case of porous film on top of oxide film, we can have three interfaces. There one interface will be oxide and porous film. So, what happens? The metal ion, so this is the metal which is forming the oxide. So, this is the metal on top of oxide films are forming. This metal ions migrates through the oxide film and comes to electrolyte, and there it dissolves. So, if the oxide film is modified, so that the diffusivity of this metal ion is reduced, so of course, it will reduce the corrosion rate of that metal. Now, in addition, apart from that, we can have few few other aspects like 2, there are electrolytes which are very good passivator. For example, HNO3, then we can have HO3 chlorate, then potassium chlorate. So, potassium permanganate, then potassium chromate. So, these are the even oxygen they can passivate easily. Now, oxygen gas passivation is nothing but if it reacts with the metal and forms an oxide layer, and that would lead to a passivation. Now, there are some self passivating elements, for example, chromium, titanium, tantalum, aluminum. These are self passivating elements because they form oxides very quickly, because they have a very high affinity to oxygen and can form oxide layer, a few nanometer thick oxide layer. And these oxides are very stable oxides and not very pervious oxide, impervious I would say. These oxides are impervious, so the diffusivity of ions will be less, and of course, it will thus reduce the corrosion rate of the metal. Now, then third is once a metal is passive, it can maintain passive state if it is not disturbed. So, once a metal becomes passive, if it is not disturbed, by some external force, it can maintain its passivity. So, I mean to say that for example, the classic example in case of Faraday's experiment, once we dip it in concentrated nitric acid and then we see that the passivation appears, and then we take that particular iron object into a dilute solution, corrosion rate is negligible. So, it maintains passivity, and it will maintain passivity if we do not scratch it. If we scratch that particular metal object, the passivity is lost and it will not go back to the passive state if we do not put it back in the concentrated acid. So, then that case, once we put a scratch in the dilute acid, it will go into the active state and maintain its active state. So, if we do not disturb, it will maintain passivity. The other classic example is, let us say one particular metal has passivated. Now, in that solution, if we had little bit of halides like chlorides, bromides, those halides are, even fluorides, those halides are not a very good thing for passive layer to maintain its passivity. And those halide ions, they attack passive layer and disturbs the passive layer and break the passive layer, and that breaking happens at localized portion. And once it happens at the localized portion, that becomes a critical, a very, very serious state, because that local region. So, for example, we have a passive layer, this is the passive layer. So, this is the layer, this is the metal surface, this is the metal surface. Once we have a kind of break into the passive layer, so let us say this is the break. So, this zone is broken. So, this zone we have exposed metal surface. So, this metal surface, this metal's portion is exposed to the electrolyte, and that can happen due to the addition of halides, chlorides or bromides, those ions. And now, around all the segments, so these particular segment are covered by the oxide film, and this small segment is exposed to the electrolyte. So, the small segment will be a small anode, and the entire region is cathode, because entire region have oxides. So, oxides can be cathodic to the metal. So, now we have a tricky situation, low anodic area, since this becomes low anodic area and around this zone you have large cathode. So, that case the dissolution rate in this portion will be extremely high. So, we can have a very rapid peat formation, and the peat growth could be autocatalytic in nature, and that can lead to failure or catastrophic failure into the material. So, one classic example is in case of stainless steel, where the breakdown of the film can happen locally, and once that breakdown happens at local positions, that local region will act as anode, and it is a small anode and large cathode around that area. So, there will be large number of cathodic reaction on the cathodic surfaces, and to maintain the electron supply to those cathodic reactions, this small anodic portion need to supply electrons to those cathodic area. So, it has to dissolve rapidly. There are few factors which can lead to passivation. One is temperature. Few factors, just to name few: temperature is an important aspect of passivation. Many cases at room temperature one metal may not be passive, but in certain electrolyte, but if we reduce the temperature it can go into passive region. For example, copper, it is not passive in concentrated HNO3, but if we reduce the temperature at room temperature of course, and if we reduce the temperature to around -11 degrees Celsius in the same acid, it passivates. So, this is one example. And then oxidizing or reducing environment. So, of course, if it is oxidizing, that environment has got oxidizing power. Many cases it can increase the corrosion rate. For example, if we add oxidant like FeCl3 in HCl, the corrosion rate of zinc increases many-fold. But many a times addition of oxidizer like let us say HNO3 is a strong oxidizer. So, that can lead to passivity. Okay. So, for example, in case of iron, strong HNO3 oxidizing agent can lead to passivity. And of course, reducing environment, it tries to break the passivity. Then third is cathodic polarization. So, we will talk about this cathodic polarization depending on sometimes if some oxidation cathodic reaction is taking place, that reaction if we modify a bit, it can either take me to active region or it can either take me to passive region, depending on how that cathodic polarization graph or the plot is intersecting with the anodic portion of that particular metal. And of course, third is abrasion or scratch. So, these are the mechanical effect which can lead to breakdown of passivity. And finally, of course, if I consider there are many other factors, I am just pointing some important aspects. Finally, ennoblement. So, ennoblement due to passivity, ennoblement happens, that means it can change its polarity. This is one instance. Other case, the metal potential can, if we have very active state, for example, iron, if it is active, the potential could be in the range of around minus 500 to 600 millivolt. That means I am talking about the corrosion potential, and even if we try to see the OCP, that means open circuit potential, it remains around 600 millivolt region when it is active. But once it becomes passive, that time potential can reach to around 400 to 300 millivolt minus. Of course, it is also in the minus range, but the potential has moved to a positive side. So, that is what it is called ennoblement. But this ennoblement can lead to problems sometimes. For example, in case of zinc coating on iron, that is a typical example of why zinc coating should not be used at a higher temperature. If the temperature reaches around 60 to 70 degrees Celsius, at room temperature or the normal temperature around 50 degrees Celsius, till 60 degrees Celsius at least, zinc acts as anode to iron, and so that is what it is a very good galvanizing material for protection of iron from corrosion. But once the temperature reaches beyond certain around 60, more than 60 to 70 degrees Celsius, zinc oxidizes and then it forms zinc oxide. Now, once zinc oxide forms, because we have this is my iron layer and this is zinc layer. So, once zinc forms, zinc remains as zinc if there is a break, small break, let us say there is a small break. So, that break region, that broken region, the iron is exposed, this is exposed, iron is exposed to the electrolyte, this is electrolyte, this is electrolyte. So, corrosion can happen, but we have already seen from the mixed potential theory that here iron preferentially acts as a cathode and zinc becomes anode. So, zinc dissolves and this section is protected, fine. But at a higher temperature around 70 degrees Celsius, the zinc, once it forms oxide, so that is this layer is forming zinc oxide. So, then zinc oxide becomes cathodic to this small segment. So, the polarity reverses. Initially zinc was anode, that means it was negative terminal in case of galvanic coupling, but once it forms zinc oxide it becomes positive. So, it becomes cathodic to the positive terminal to the small opening into that layer or the coating. So, that case this segment will dissolve rapidly, and zinc oxide will remain as a cathodic layer. So, these are some of the criteria or the statements which are very true for when we discuss passivity. So, we will keep discussing more about passivity. So, let me stop here. We will continue our discussion on passivity in subsequent lectures. Thank you very much.